Oh, hello.
I'm here to talk to you about the physics lecture at Georgia Tech this year on gravity waves. Oh, hello there. I'm also here to talk to you today about gravitational waves.
What are gravitational waves?
Tiny ripples in the fabric of space-time. That is what gravitational waves are.
Alright, let's just start our discussion off on relativity.
What is relativity? Well, relativity means many things, but we are viewing relativity from the view of an astrophysicist. So what does this encompass?
We are encompassing the cosmos.
We were told from the talk that astrophysicists care about these specific topics.
Black holes, gravitational waves, and cosmology and the expanding universe.
So this was a significant talk for us because it was the first or second day the Einstein statue was on campus. So let's talk a little bit about Einstein. 110 years ago, to the day of the talk on gravitational waves given at Tech, Einstein published his papers on the photoelectric effect, Brownian motion, and special relativity. Those three are easy to remember if you just remember PBS, photoelectric effect, Brownian motion, and special relativity. That's how you remember it, PBS. They also gave us a famous quote from Einstein that it made an impact enough for me to take down. He said, "I realized all natural phenomenon could be discussed as special relativity except for gravitation. That's the one that can't." Before we could delve into our talk about gravity waves, we needed some background on Einstein, his general theory of relativity, his special theory of relativity, and how he felt about gravity. They told us Einstein regarded gravity as just a generalization of relativity, hence the name general relativity. The physicists explained to us that space-time curvature tells matter how to move, while matter tells space-time how to be curved. They're coupled in an equation Einstein wrote out that I believe was outside the scope of the lecture. Well, what does this imply? This implies that gravity and where you are in a gravitational field affects how your clock ticks. The physicists also decided to express time moving at different speeds as someone being younger or older, which in my mind just overcomplicated the whole thing. It was easier to just think about the clock being slower or faster. This can lead us into the discussion of gravitational waves.
In the lecture, the topic of how gravitational waves were formed.
This led us down the proverbial rabbit holes, you would say, on discussion concerning black holes. What did we learn in this lecture about black holes, you would say? Well, we learned that black holes are the end result of some stars' life cycles. Other end results include white dwarfs, neutron stars, etc. We also learned that black holes are detected by how matter interacts with them.
The last topic that we went on concerning black holes was the topic of two black holes colliding with each other. I mean, just wow. Could you imagine that happening?
We also got a very cool demonstration of the two black holes colliding and the sound it makes. It went a little like this.
We now know the source of gravitational waves. It's when two black holes collide. But again, these are all theoreticals. They told us a couple times during the lecture, there's no proof that gravitational waves actually exist, but the probability is, and the data says that they do.
So how do we detect gravitational waves? First of all, we know that they travel at the speed of light.
But we still have laser interferometers in space that are supposed to detect these gravitational waves. And we have various centers around the world also trying to detect gravitational waves. They told us we have to put them in space, though, because the Earth's gravitational field and the spin of the Earth affects our detection of gravity. They gave us an analogy that detecting a gravitational wave requires the same precision. Picture a human hair, and they said that to detect a gravitational wave is going to take the same precision that if you were to measure from Earth to Jupiter and be off by the piece of hair. That's how hard it is to detect the gravitation. Never heard of gravity waves before, and I thought going to the talk would be interesting to hear another piece of Einstein's theory of relativity beyond what the layman knows. So I thought I was looking forward to learning about them, but I was a little underwhelmed because it seemed like the presenters couldn't go too far into the mathematics of gravity waves because it was too complicated, and they couldn't go too far into the theory because it was too complicated. So we got just a taste of both.
Alright, digging a little deeper on the subject of gravitational waves, there was an article that was found, published December 1st, talking about the LISA Pathfinder mission, which is set to detect gravitational waves in deep space. Now this mission was delayed till December 3rd, which is today.
It will put two test masses in a near perfect gravitational freefall and control and measure their motion with unprecedented accuracy by its inertial sensors, the laser metrology system, the drag-free control system, and the ultra-precise micropropulsion system.
This experiment setup will make it easier for gravitational waves to be detected if any ever decide to pass through within the range of our sensor.